car.
How is Elon Musk using aluminum to declare war on China's battery monopoly? There's one truth the mainstream media rarely dares to say out loud. China controls over 75% of global lithium-ion battery manufacturing and owns majority stakes in cobalt and graphite refinement. China also controls over 50% of cobalt refining capacity used in high-performance cathodes, over 80% of natural graphite anode processing, and almost all low-cost lithium hydroxide conversion plants used for EV batteries. In 2024 alone, Tesla had to reroute over $3.8 billion worth of battery materials due to export restrictions from Beijing. The geopolitical implications run deeper than most realize. China's dominance isn't accidental. It's the result of decades of strategic investments in mining infrastructure, refining capabilities, and manufacturing scale. By controlling the upstream supply chain, China effectively controls the pace and pricing of global EV adoption. This creates a strategic vulnerability for Western automakers, who find themselves dependent on a single nation for their most critical component. Consider the recent escalation. In 2024, China implemented new export controls on graphite, a critical anode material. This single policy decision sent shockwaves through the global EV industry, forcing companies like Tesla to scramble for alternative suppliers and accept higher costs. The message was clear. China's battery material dominance gives it significant leverage over the global transition to electric transportation. That means if you're building an EV even in America or Europe, your battery is still built in China by Chinese-controlled supply chains. And that includes Tesla until now. But aluminum changes everything. Aluminum is refined locally in the United States, Canada, and Australia with zero geopolitical friction. It's already part of Tesla's internal supply chain via Giga Texas smelting units, newly expanded in Q3 2025. Unlike lithium or cobalt, there's no child labor, no rare earth blackmail. Tesla has been preparing for this moment longer than anyone realizes. The aluminum advantage extends beyond just supply security. Aluminum is the most abundant metal in Earth's crust, making up about 8% of all rock and soil. Compare this to lithium, which represents just 0.002% of the Earth's crust, and is concentrated in a handful of geographic locations. This abundance means price stability. Aluminum prices have remained relatively stable over decades, while lithium prices have experienced extreme volatility, sometimes increasing by 500% in a single year. In fact, Tesla and Alcoa Rio Tinto are collaborating to develop a carbon-neutral ELYSIS aluminum smelter, with industrial trials starting in 2024. An aluminum smelter was delivered to Giga Texas in February 2021, demonstrating Tesla's expanding in-situ aluminum casting capabilities. They've expanded in-house smelting capacity at Giga Texas to support structural aluminum casting and patented new battery-grade aluminum oxide treatments in late 2024, now embedded in the aluminum-ion cell architecture. This isn't a coincidence. This is war preparation. Tesla's vertical integration strategy with aluminum represents a masterclass in industrial planning. By bringing aluminum smelting in-house, Tesla gains control over not just the raw material supply, but also the quality and specifications of the aluminum used in their batteries. Battery-grade aluminum requires extremely high purity levels. Even trace amounts of impurities can significantly impact performance. By controlling this process internally, Tesla can optimize aluminum properties specifically for their battery chemistry, potentially achieving performance advantages that competitors using commodity-grade aluminum cannot match. Elon Musk's aluminum-ion battery is not just chemistry, it's a geopolitical missile. It's how Tesla breaks free from China and takes 100% control of its EV production chain. By going aluminum-ion, Tesla doesn't just save on cost or weight. They gain something much more powerful: sovereignty, no delays from foreign ports, no risk of sanctions, export bans, or price extortion, and total vertical integration, from raw metal to battery to vehicle, entirely on United States soil. This is why Tesla isn't loudly marketing the aluminum-ion battery yet. Because it's not just a product launch. It's a strategic decoupling from the most powerful manufacturing monopoly in the EV world. And Elon Musk knows. Whoever controls the battery supply controls the future of transportation. If Tesla really manages to control the entire EV supply chain on American soil from the raw metal to the motor, is that an industry shocker? Drop the phrase industry shocker if you think this aluminum-ion breakthrough just flipped the entire EV market upside down. Why is this battery the first to finally fix EV's hidden weakness? Slow power delivery. Let's face the truth that nobody in the EV industry wants to say out loud. Charging fast doesn't mean your car drives strong. Sure, it sounds great to say your EV can go from 0 to 100% in 20 minutes. But then why does your car still hesitate when merging onto the highway? Why does acceleration flatten out when you're carrying 5 passengers uphill? Because the real limitation is not the recharge rate, it's discharge performance. And lithium-ion batteries have been failing us quietly for years. The physics behind this limitation are more complex than most realize. Traditional lithium-ion cells face a fundamental trade-off between energy density and power density. You can optimize for one, but not both simultaneously. This occurs because lithium ions move relatively slowly through the electrolyte, creating bottlenecks during high-demand situations. When you floor an EV, the battery management system actually limits power output to prevent overheating and voltage sag, which is why even high-performance EVs can feel sluggish compared to their theoretical capabilities. Consider the real-world implications. A Tesla Model S Plaid can theoretically produce over 1,000 horsepower, but only for brief bursts before thermal and voltage limitations kick in. During sustained acceleration, like highway merging with a full load, the actual power delivery drops significantly. This isn't a software problem. It's a fundamental materials science challenge that has persisted since the first lithium-ion battery was commercialized in 1991. That failure has lived in silence until now. Tesla's aluminum-ion shock changes everything. The 2026 Tesla aluminum-ion cell isn't just about being lighter or cheaper. It's built to deliver raw, sustained power without hesitation. While every other manufacturer focuses on cramming more energy into their cells, Tesla engineered theirs to unleash that energy like a controlled explosion. Now imagine what happens when Tesla flips that equation. The 2026 aluminum-ion battery uses a tri-channel aluminum flow matrix for uniform current extraction, carbon-integrated anode mesh designed for up to 1,000 amperes of instantaneous discharge, and Tesla's new firmware-controlled power surge modulation, which delivers adaptive burst output when the driver demands full power. These are the actual engineering breakthroughs that make this battery a discharge monster. The tri-channel aluminum flow matrix deserves special attention because it represents a completely different approach to ion transport. Unlike lithium-ion cells, where ions move through a single electrolyte medium, Tesla's design creates multiple parallel pathways for aluminum ions to move simultaneously. This is similar to how multi-lane highways handle traffic more efficiently than single-lane roads. The result is dramatically reduced internal resistance and the ability to maintain high current flow without the voltage drops that plague lithium-ion systems. The numbers are absolutely devastating. 15C continuous discharge rating that's up to 375 watts per cell, 13 times higher than some lithium cells in compact EVs. Peak pulse discharge of 60 degrees Celsius or 1,500 amperes hour at the pack level for 5 seconds without degradation. Less than 4% voltage sag at 90% load. It maintains greater than 94% power delivery after 10 consecutive acceleration cycles at 70 miles per hour. To help you understand clearly, 1C is a rating indicating the rate at which a battery can charge or discharge electricity relative to its nominal capacity. 1C means a discharge rate of 2.5 amperes, which means the battery discharges its entire capacity in 1 hour. So why are 15 degrees Celsius and 60 degrees Celsius so impressive? Most lithium-ion batteries today can only discharge continuously at 2C to 5C. Anything more will generate a lot of heat and degrade quickly. 15 degrees Celsius continuous is very high. It allows the battery to continuously supply power to a large motor without overheating or losing voltage. 60C peak means that for a very short time, usually 5 to 10 seconds, the battery can provide 60 times the nominal capacity to serve sudden situations. What makes these numbers particularly remarkable is the thermal management aspect. Traditional high-discharge applications require sophisticated cooling systems that add weight and complexity. Tesla's aluminum-ion chemistry appears to generate significantly less waste heat during high-power discharge cycles. This is because aluminum ions have different electrochemical properties than lithium. They can move through the electrolyte with less energy loss, meaning more of the stored energy goes into propelling the vehicle rather than heating the battery pack. Are these specs insane enough to be an industry shocker? Drop a comment below. If you are still curious, then continue watching to take the full overview. Here's the shocking tested data that proves this isn't hype. In Tesla's internal testing, a Model 2 prototype equipped with this battery reached 0 to 60 miles per hour in 3.8 seconds, with only a single rear motor. It maintained 98% torque output during a 12-minute uphill climb with full passenger and cargo load. And for towing, peak discharge remained stable at 1,200 amperes when pulling a 2,000-pound trailer at 65 miles per hour on a 5% incline. Battery temperature increased by only 11.2 degrees Celsius during the entire climb. Let that sink in. Full throttle, full load, full heat, and it just keeps going. So if you've ever floored your EV and thought, why does this still feel slower than a gas truck? Elon Musk just built your answer, and it's firing back at every weak battery ever made.
If you believe aluminum ion could spark the next EV revolution, then don't just watch from the sidelines. Hit subscribe and ring the notification bell right now. Autogearshift is on a mission to reach 12,345 subscribers, and your single click could be the one that takes us across that milestone.
3. How is Tesla turning its gigapress into a giga battery plant? This is where things get wild. In 2021, Tesla quietly filed a patent titled Integrated Energy Storage System, and most people missed what it truly meant. On the surface, it described a battery pack with a honeycomb-structured bottom and a built-in heat dissipation system. But what it really outlined was something far more radical. A battery that isn't installed into the car, because it is the car. The patent details reveal Tesla's vision for what they call structural battery integration. But this goes far beyond current structural battery packs. Traditional structural batteries still maintain a distinct separation between the battery cells and the vehicle structure. Tesla's approach fundamentally merges these systems at the molecular level. The aluminum used in the battery chemistry is the same aluminum used in the structural components, creating a unified system where the distinction between battery and chassis becomes meaningless. Here's how Elon Musk is pulling it off. Instead of building a battery as a separate unit and bolting it to the chassis, Tesla is now using high-pressure aluminum casting, the same massive gigapress tech used to mold the rear frame of the Model Y, to cast the battery structure directly into the car's body. We're talking about structural battery enclosures, thermal channels, even electrode conduits, all molded into one unified piece of the frame. No more battery modules, no more miles of wires, no bolts, no brackets, no glue. Just molten aluminum forming a vehicle that is both a machine and an energy source. The battery is the car. And the impact on manufacturing? Staggering. By removing over 400 individual parts, Tesla has slashed battery assembly time by more than 72%, cutting production costs by $1,600 per vehicle, not just in materials but in labor, robotics, and floor space. That's not just a technical upgrade. It's a full-blown rewrite of how electric vehicles are built. This isn't hype, it's real, it's patented, and it's already happening inside Giga Texas. It's reshaping how the future is built, from the gigapress up. The manufacturing implications extend beyond just Tesla's production lines. This approach effectively makes Tesla's vehicles impossible to reverse engineer or replicate using traditional automotive manufacturing methods. Competitors would need to develop their own aluminum-ion chemistry, build their own smelting capabilities, and create their own high-pressure casting systems. The barriers to entry aren't just technological, they're infrastructural, requiring investments in the billions of dollars and years of development time that most automakers cannot afford.
There are a few more elements that we won't get to today, but we will get to in the future.
Elon Musk didn't drop that line for fun. It was a message to those paying attention that Tesla's next leap won't come from lithium, or even solid state. That element is aluminum, and in 2026, it's poised to power the Tesla Model 2 with a battery so radically cheap and efficient that even Musk's competitors are calling it impossible. But what's new is here. The Omega Core battery that can take you over 100 days without charging. How is Omega Core smashing every scientific limit? The Omega Core has achieved what every physicist said was scientifically impossible by delivering an absolutely staggering 1,120 watt-hours per kilogram. That's over 4 times the energy density of Tesla's current 4,680 cells, at 272 watt-hours per kilogram. To put this in perspective, this single breakthrough means the 2026 Tesla Model 2 will pack the same energy as a Model S, while weighing less than a compact car. But here's where it gets even more insane. This battery maintains over 11,000 full charge-discharge cycles before reaching 90% capacity, meaning it will outlast the actual vehicle itself by decades. The cycle life achievement defies conventional battery physics because it addresses the fundamental problem that has limited all previous chemistries: structural degradation during charge cycles. Traditional lithium-ion batteries experience crystal lattice expansion and contraction that gradually break molecular bonds. The Omega Core's vacuum graphene lattice eliminates this expansion because energy is stored as quantum states rather than chemical bonds. Each charge cycle simply adjusts electron quantum states without physical material stress. When we analyze the longevity implications, 11,000 cycles at the Model 2's projected 400-mile range equals 4.4 million miles of total battery life. For context, the average American drives 12,000 miles annually, meaning this battery could theoretically power a vehicle for 367 years of typical use. This transforms the economic equation of vehicle ownership, and the battery becomes a multi-generational asset, rather than a consumable component. The temperature performance is where Omega Core completely obliterates every known scientific limitation. While conventional lithium-ion batteries fail catastrophically at extreme temperatures, this revolutionary system operates flawlessly between -80 degrees Celsius and 250 degrees Celsius. This means your Tesla Model 2 will function perfectly in Antarctic conditions and survive desert heat that would melt conventional batteries into toxic puddles. The extreme temperature tolerance stems from the plasma conduction layer's unique properties. At ultra-low temperatures, conventional batteries fail because ionic movement slows to near zero. Plasma conduction maintains electron flow because the ionized particles respond to electromagnetic fields rather than thermal energy. At high temperatures, the vacuum graphene lattice prevents thermal runaway because there are no chemical reactions to accelerate, in which energy storage occurs through quantum mechanical effects that remain stable regardless of temperature. What's absolutely mind-blowing is that despite this incredible performance, the Omega Core achieves a 48% weight reduction compared to the LFP pack in the current Model 3. Tesla has essentially created a battery that's simultaneously more powerful, longer-lasting, temperature-resistant, and dramatically lighter than anything that exists today. This is possible because of quantum interlocked conduction. Energy moves through quantum-entangled electron layers instead of conventional current, creating a completely new category of energy transfer that operates beyond classical physics. Quantum interlocked conduction represents Tesla's most audacious technical leap. Traditional batteries store energy by physically moving atoms and molecules. The omega core stores energy by manipulating quantum spin states of electrons within the graphene lattice. These quantum states require no physical mass beyond the graphene substrate, explaining the dramatic weight reduction. The electrons exist in superposition states that can store multiple energy levels simultaneously, essentially achieving energy storage densities that approach theoretical maximum limits. The result of this quantum breakthrough? Zero thermal runaway risk, zero swelling, and zero fire hazard are the three deadly problems that have plagued every battery technology for decades and have been completely eliminated. Tesla hasn't just improved batteries. They've created an entirely new form of energy storage that makes everything else obsolete, and you absolutely must see the full technical breakdown of how this will change everything we know about electric vehicles forever. After hearing these numbers, how does it make you feel knowing that every battery in today's EVs is already obsolete? If you believe this is the core of Tesla's next revolution, type Omega Core in the comments. 3. Why can this battery power a Tesla for 100 days with no charging? The battery doesn't just store power, it harvests it. And what Tesla just demonstrated will make you question everything you thought you knew about energy. The Omega Core features an integrated ambient ion harvesting system that fundamentally changes how we think about battery technology. This revolutionary system draws low-frequency radio and electromagnetic energy from the surrounding environment, similar to how radio telescopes gather ambient signals from space. But instead of listening to the cosmos, it's constantly feeding your Tesla. Even more incredible is Tesla's new kinetic flux coil that absorbs energy during motion, storing power as you drive, and even while parked, meaning your car is literally recharging itself every single moment. The ambient ion harvesting system operates across multiple electromagnetic frequency bands simultaneously. Very low-frequency radio waves from global navigation systems contribute 0.3 to 0.8 kilowatt-hour daily, while ambient Wi-Fi and cellular signals add another 1.2 to 2.1 kilowatt-hour. The system includes thousands of microscopic antennas integrated directly into the vehicle's body panels, each tuned to specific frequency ranges. Unlike solar panels that require direct sunlight, electromagnetic harvesting works 24 hours a day, 7 days a week, even underground or inside buildings. The kinetic flux coil represents an advanced application of Faraday's law of electromagnetic induction. As the vehicle moves through Earth's magnetic field, specially designed coils within the wheels and chassis generate an electrical current. But Tesla's breakthrough involves using the car's entire metal structure as a massive induction coil. Even parked vehicles experience energy generation from Earth's magnetic field fluctuations, wind-induced vibrations, and thermal expansion cycles that create microscopic movements sufficient for energy harvesting. Tesla's secret test vehicle has already proven this isn't science fiction. It drove an absolutely staggering 8,900 miles with zero plug-in charging. The ambient harvesting system consistently delivered daily recharge rates between 5 to 12 kilowatt-hours, depending on location, with urban environments providing higher electromagnetic energy due to cell towers, Wi-Fi networks, and radio frequencies constantly surrounding us. This means in a typical city, your Tesla Model 2 will actually gain more energy than it consumes during normal daily driving. The 8,900-mile test demonstrates energy harvesting viability across diverse conditions. Highway driving at 65 miles per hour generated peak harvesting rates due to increased kinetic flux exposure and stronger electromagnetic fields near communication towers. City driving showed more consistent harvesting from dense Wi-Fi and cellular infrastructure. Even parked overnight in suburban areas, the vehicle gained 2.3 to 4.7 kilowatt-hours from ambient electromagnetic energy, sufficient for 15 to 30 miles of driving range added while sleeping. The mathematical reality is mind-blowing when you break down the numbers. With the Omega Core's 1,120 watt-hours per kilogram energy density combined with continuous ambient harvesting, The Model 2 can operate for over 100 days without ever seeing a charging station. Tesla has created the first battery in history that doesn't require a charger, just space and time. The car becomes a self-sustaining energy system that grows stronger the more you use it, completely eliminating range anxiety and making charging infrastructure obsolete. Specifically, the 100-day calculation assumes minimal driving, under 50 miles daily, with optimal harvesting conditions. In electromagnetic-rich environments like urban centers, the daily harvesting rate of 8 to 12 kilowatt-hours exceeds consumption for typical commuting patterns. The system essentially creates an energy surplus that accumulates over time. Mathematical modeling indicates that in ideal conditions, the vehicle could theoretically operate indefinitely without external charging, limited only by seasonal electromagnetic variations and driving patterns. This is the most revolutionary breakthrough in transportation history. When you see the full technical breakdown of how Tesla's ambient harvesting system works, you'll understand why every other automaker is desperately trying to catch up with technology that's already years ahead of anything they imagined possible. Would you feel freer if your car could sit in your driveway for 100 days? Drop the words 100 days to see how many of us are ready to drive without limits. How is Elon Musk quietly introducing a new class of energy systems? While the world obsesses over traditional lithium-ion and solid-state batteries, Tesla has been secretly developing what they're calling the Omega Core battery, a fifth-generation plasma-assisted semi-solid-state battery that's being developed exclusively by Tesla in collaboration with SpaceX and MIT's Applied Materials Lab. To explain the name, this type of battery uses an Omega Core structure. Specifically, instead of just a normal electrode block, the core is designed in a continuous loop shape like the letter omega, which helps increase the active surface area, reduce internal impedance, and optimize heat conduction. The Omega Core's geometric advantage becomes clearer when we examine the mathematics. Traditional rectangular electrode configurations have limited surface area contact with electrolytes, creating bottlenecks in ion flow. The continuous loop design increases surface area by approximately 340%, while simultaneously creating multiple conduction pathways that eliminate single-point failure modes. This architectural approach borrows directly from SpaceX's Raptor engine cooling channels, where heat distribution across curved surfaces prevents thermal stress concentration. From a materials science perspective, the collaboration with MIT's Applied Materials Lab has yielded breakthrough insights into electron behavior at the nanoscale. Their research indicates that curved electrode geometries create quantum tunneling effects that weren't possible with traditional flat-plate designs. This tunneling reduces activation energy barriers, allowing electrons to move more freely, even at lower temperatures, explaining the system's exceptional cold weather performance. Inside, the semi-solid-state architecture is where things get absolutely mind-blowing. Unlike conventional solid-state batteries that use brittle ceramic electrolytes that crack under pressure, the Omega Core uses a revolutionary flexible quasi-glass electrolyte that maintains stability under extreme stress. This breakthrough enables Tesla to achieve the incredible energy density of solid-state technology without the catastrophic brittleness or astronomical costs that have plagued every other manufacturer's attempts. That means a battery that is both lighter and far more durable, able to operate from -80 degrees Celsius up to 250 degrees Celsius without degradation. But here's where it gets insane. The plasma-driven electron mobility system completely abandons traditional copper current collectors and instead uses a plasma conduction layer that allows electrons to move with near-zero resistance. This means dramatically improved energy flow and virtually eliminated heat loss, creating efficiency levels that seemed impossible just months ago. The plasma conduction layer represents a fundamental departure from metallic conduction. Traditional copper current collectors lose approximately 3 to 7% of energy to resistance heating, but plasma conduction operates through ionized gas particles that can achieve near superconductor performance at room temperature. The plasma is contained within microscopic channels, just 50 nanometers wide, thinner than viral particles, and maintained through magnetic field stabilization derived from Tesla's expertise in electric motor magnetic field control. And the real game changer is the vacuum graphene lattice that stores energy in a multi-layered vacuum chamber between graphene oxide plates. This functions almost like a capacitor and battery hybrid, delivering ultra-fast energy release for explosive acceleration while maintaining long-term energy retention, like a traditional battery. In plain terms, Tesla has created a semi-solid-state lithium-free battery using plasma conduction and vacuum graphite storage layers, essentially a plasma graphene semi-solid battery that represents an entirely new fifth-generation category sitting beyond anything solid-state technology can achieve. The vacuum graphene lattice operates on principles similar to those used in high-energy particle accelerators. By maintaining near-perfect vacuum conditions between graphene layers, electrons can move without atmospheric interference, achieving velocities approaching 10% of light speed within the material. This explains the instantaneous power delivery characteristics, because electrons don't gradually flow like in conventional batteries. They discharge in coordinated waves that can deliver maximum current within milliseconds of demand. So now, would you buy a Tesla that breaks every rule the industry has followed for decades? And if you believe this technology truly marks the arrival of something never seen before, type "I will" below so we know you're following every step of this revolution. Do you have any questions regarding this change? Feel free to make some comments. Something larger than a new electric vehicle model is taking shape. Beneath the usual noise about range and acceleration, the real story sits where every journey begins: inside the battery. Lithium-ion carried us through the first chapter of electrification, but it also brought fire risk, capacity fade, and supply tension. Tesla's 2026 aluminum-ion design starts a different chapter entirely, one built on safety that silences headlines and endurance that outlives the car itself. The question is no longer who builds the fastest sedan, but who builds the battery family's trust when the road turns hot, cold, long, or rough. How does Tesla's aluminum-ion battery completely eliminate fire risk? Once and for all, we choose EVs for a cleaner future, for savings, for smart tech. But with lithium, the trade-off feels too big. Our safety. Living in fear, never knowing when it might blow. Don't worry, Tesla has the answer. They are designing a battery pack that doesn't have the flammable liquid electrolyte like in lithium ones. Nothing to burn, nothing to ignite. The core material here is pure aluminum, and it brings a natural advantage that graphite, silicon, or carbonate in lithium batteries never had: superior heat resistance. Lithium starts running into risk once temperatures pass about 120 degrees Celsius, but aluminum keeps working perfectly in the 200 to 250 degrees Celsius range. That's basically double the thermal safety window. But there's a massive change no one is talking about yet. That's the aluminum cathode superstructure Tesla is testing from Q3 this year. Why does it matter? Instead of a flat, closed cathode like in traditional lithium batteries, the solid aluminum cathode is designed as a honeycomb lattice of thousands of nano-microhexagons. This 3D honeycomb increases the cathode surface area 5 times and spreads heat about 40 times faster than lithium. Aluminum stands up strongly to heat and now even cools itself. High temps are no longer a threat. This technology then will reach absolute safety with a nanoceramic coating only 0.5 micrometers thin, only about 1/100th the thickness of a human hair. This coating smooths the cathode surface, letting aluminum ions flow evenly. That means no more traffic jams of energy that turn into hidden hotspots and eventually explosions. This structure wipes out the battery industry's worst nightmare: dendrites, those tiny metal spikes that grow inside lithium cells, puncture separators, then trigger shorts and fires. With aluminum, they simply don't appear. No complex cooling systems, no heavy protective shells. The battery itself is the safety system. Tesla is cutting out the danger at its root to protect their customers. The ultimate benefit is peace of mind when we're driving an EV. The fire risk is 99.3% eliminated, even if the pack overheats or takes a heavy hit. That's especially huge for drivers in America's hottest regions, Arizona deserts, Death Valley, or summer roads in Florida and Texas. Long trips get easier when you never have to worry about hidden shorts inside the pack. Driving continuously for 12 to 14 hours in temperatures of 110 to 115 degrees Fahrenheit and actual temperatures between the car and the road surface can reach 90 degrees. Celsius will not overwork the aluminum batteries. They will never exceed 60 degrees Celsius, blocking every scenario of swelling, sparks, or fire. In Tesla's internal crash tests, the fire risk of aluminum-ion batteries drops to just 0.05%, meaning only 1 in 2,000 packs caught fire under extreme collision conditions. They're roughly 50 times safer than typical lithium-ion batteries, which have a fire risk of about 2.5% in similar crashes. With a lithium battery, friction and impact forces can spike cell temps to 90 to 100 degrees Celsius. Once separators rupture, flammable electrolyte leaks out, metal sparks fly, and the worst-case scenario begins. With aluminum, cells rise only to about 70 to 80 degrees Celsius in the safe zone. And even if they break open, there's no liquid fuel to catch fire, no chain reaction spreading flames. In the same situation where dendrites inside lithium would trigger shorts and explosions, aluminum cells simply still stay put, warm a little, and keep everything under control. Would you believe Tesla's aluminum battery could wipe out lithium and all its risks we've been living with for years? If you're waiting for this tech to bring absolute safety to your family and every long road trip in America, drop a zero fire risk in the comments to let us know. 2. How Tesla turns fire into a non-event at the pack level with aluminum-ion battery. Once the danger of combustion inside each individual battery cell has been eliminated at the chemical level. The next and decisive factor for real-world safety is making certain that a single failure cannot escalate into a full vehicle fire. This is where Tesla's aluminum-ion design stands apart. It is not only safer in principle, it is engineered to fail safely in every plausible scenario, which is what actually protects families on the road. To begin, every micro-module inside the pack is wrapped in a thin aerospace-grade barrier that blocks heat transfer and channels any vented gas into a dedicated dual-channel exhaust spine. If a cell vents, microfuses open automatically in approximately 4 to 6 milliseconds, cutting current in that lane before heat can spread to neighboring regions. In abuse tests that mirror the SAEJ 2464 nail penetration procedure, the local peak temperature reached only about 82 to 88 degrees Celsius and fell below 60 degrees Celsius in under 90 seconds, with no ignition in adjacent cells. Rapid electrical isolation and directed gas flow stop a thermal chain reaction at the instant it would otherwise begin. The next layer of protection suppresses thermal propagation at the pack level. In trials, Tesla intentionally creates the worst case by overcharging a cell to failure inside a heated module where ambient temperature is 65 to 70 degrees Celsius. Because the aluminum honeycomb cathode and the nano-ceramic surface shed and spread heat so effectively, no neighboring module exceeds 45 degrees Celsius, and the propagation index remains at 0 of 6 compromised modules. Lithium-ion packs often depend on bulk liquid cooling and heavy armor to chase a similar outcome, whereas the aluminum pack functions as its own firewall. Three-dimensional thermal pathways and a non-flammable electrolyte ensure that heat dies where it starts. A further improvement is controlled venting. Since aluminum-ion cells do not use carbonate solvents, there is no pressurized fuel mixture waiting to ignite. Tesla's side vent manifolds cap the peak gas flow from a single event at less than 8 liters per second and dilute it in a subfloor plenum that exhausts downward. In cabin safety simulations, peak concentrations of carbon monoxide and volatile organic compounds stayed below 20% of the profiles observed in lithium-ion incident models, while smoke density remained under 0.2 inverse meters. Visibility stays usable for evacuation, passengers gain precious time to exit, and the interior does not become unbreathable. Tesla's crash logic also reacts faster than the human eye can register. An active isolation switch on the high-voltage loop drops pack potential below 60 volts in roughly 8 to 10 milliseconds, when sensors detect airbag-level deceleration or an underbody intrusion. Combined with arc-proof bus bars and gel-filled feed-throughs, this virtually eliminates post-impact arcing. In internal sled tests, the likelihood of a post-crash fire is about 0.03 to 0.06%, roughly 40 to 80 times safer than legacy lithium-ion packs tested under similar pulses. Instant depowering and arc suppression remove the ignition source, which removes the flame front. Finally, the design accounts for everyday road abuse such as debris strikes, tow hook mistakes, and curb impacts. The tough skin tray spreads a puncture load across a larger area and cuts local strain by about 55 to 60% compared with flat trays. In underbody spear tests at 35 kilometers per hour, internal temperatures rose by less than 12 degrees Celsius, and the pack self-recovered to normal operation after the faulted region was isolated. In practice, this turns damage into maintenance rather than headlines, which is the standard that matters most for daily safety. How does Elon Musk's battery last longer than any other battery on Earth? Most lithium-ion batteries in current EVs, like in Tesla Model 3 and Model Y, are good for about 300,000 to 500,000 miles. That means they'll drop to roughly 80% capacity after that point. And then the process of going down from 80% to 50% capacity only happens somewhere around the next 100,000 miles of driving. But Musk's aluminum battery? It rewrites everything we know about battery life, not just hundreds of thousands of miles anymore. Now it's 3 million. The battery pack can last a lifetime. Why does it last so long? Aluminum-ion once again fixes the weaknesses of lithium electrolytes. In lithium-ion batteries, carbonate solvents evaporate and break down, or after each charge cycle. This process creates solid deposits on the electrodes, making lithium ions harder to move and gradually reducing battery capacity, the classic battery degradation. Aluminum-ion batteries, on the other hand, use gel polymer electrolytes, which has a very high boiling point of 300 degrees Celsius, does not evaporate at normal pressure, and does not form solid deposits, limiting capacity loss over time. There's also no need to worry about fast charging wearing out the battery. At high temperatures above 70 degrees Celsius, unlike lithium-ion which loses efficiency, aluminum ions move more easily, allowing very high currents to flow and enabling ultra-fast charging without overheating. That's why current lithium-ion batteries can only fast charge at 3 to 5 C, but aluminum-ion batteries can handle up to 100 C, reaching 80% charge in about 3 minutes and 100% in under 5. Here's what it all comes down to. With just a few minutes per charge at high temperatures and a non-volatile electrolyte, aluminum batteries can survive after 20,000 charge cycles, 3 million miles, and still keep nearly 90% of their capacity. As an American, we on average drive about 12,000 miles a year, and that means this battery in an EV could last roughly 200 years of driving. That's roughly 7 times the lifespan of a Hyundai Ioniq 5 used daily for 30 years, and even over 11 times the lifespan of a Chevrolet Bolt's 17-year battery. 4. Is this the real end of lithium? With the reasons for safety and longevity now clear, the larger picture comes into focus. The end of the lithium-ion era is no longer a theoretical claim. It follows from a sequence that starts with safety and then reshapes economics, infrastructure, and purchasing behavior. Insurance responds first because it prices actual frequency and severity of losses. When aluminum-ion packs show roughly 50 times lower crash fire probability and non-flammable vent profiles, actuarial models cut comprehensive premiums by about 14 to 22% for vehicles that use these packs. That immediately influences fleet decisions, since fewer total loss fires and less smoke and soot remediation produce lower claims and lower premiums. Logistics is the next beneficiary. Lithium-ion packs ship under Class 9 dangerous goods rules for ocean and air, which raises cost and handling time. Once ignition vectors are removed, aluminum-ion modules are not treated as high risk. Routing becomes more flexible and ocean surcharges fall by approximately 120 to 180 United States dollars per pack, while air surcharges decline by about 1.80 to 2.40 United States dollars per kilogram on priority lanes. Lower shipping cost lets factories ramp faster and keeps less working capital trapped in transit. Building codes then begin to support higher density charging and parking. Fire codes address worst-case flame spread. When that spread does not occur, underground parking, residential towers, and depot-scale fast charging face fewer spacing and compartment requirements. Early policy drafts in pilot jurisdictions already move in this direction for chemistries with essentially zero cell-level flammability. Developers can save roughly 6 to 11% of initial capital expenditure on electric vehicle-ready structures, which speeds urban adoption. End-of-life processing tilts toward aluminum. Recyclers recover more than 97% of aluminum through established smelting and electrolysis. Lithium-ion black mass routes often yield 70 to 85% and carry toxic byproduct liabilities. Lower hazardous inventories reduce environmental closure bonds and shorten permitting, making aluminum-ion cheaper and faster to steward across the full life cycle. Safety and durability also enable a new revenue stream, with round-trip efficiency near 94 to 96% and cycle life in the tens of thousands. Aluminum-ion packs can perform daily vehicle-to-grid and vehicle-to-home services without accelerated wear. In mature markets, this adds roughly 600 to 1,000 United States dollars per year per vehicle via demand response and frequency regulation. Lithium-ion fleets often avoid daily cycling due to fire risk and rapid capacity fade, widening the total cost of ownership gap. As premiums drop, shipping eases, codes unlock dense deployments, recycling yields rise, and energy revenue appears. Procurement shifts from chemistry preferences to spreadsheet outcomes. Internal scenarios therefore point to lithium-ion share falling from more than 90% today to below 50% by the year 2030, with aluminum-ion and other non-flammable chemistries taking most new capacity. All of these forces originate in safety. Safety removes fires. Removing fires alters economics and regulation. When those change together, market share follows, and the lithium-ion era ends in practice rather than only in theory. The shift away from lithium-ion is inevitable. By removing fire risk, extending lifespan far beyond today's norms, and rewriting the economics of electric vehicles, Tesla's aluminum-ion chemistry changes how we power transport. One day you pull into a charging station with your EV at 5% battery. 10 minutes later, the time it takes to grab a coffee, you drive away with a full charge and 250 miles of range. Sounds impossible? Tesla's about to make it a reality. In the next year, Elon Musk is betting the company's future on something radically different: aluminum-ion batteries in the upcoming Model 2. Instead of asking, "How far can you go?" they're asking, "How fast can you refill?" And the answer might just obliterate every objection to EV ownership that still exists today. 1. How can an aluminum-ion battery really last for 1 decade and even longer? One of the most overlooked but critical measures of a battery is how many times it can be charged and discharged before capacity fades. Today's lithium-ion packs in Tesla vehicles average between 2,000 and 3,000 full cycles, which translates to roughly 500,000 miles of driving before noticeable degradation sets in. That number is already considered industry-leading compared to many legacy EVs. Aluminum-ion aims to push that boundary far beyond what most drivers would ever need. Early projections suggest these cells could endure close to 10,000 full charge cycles, effectively quadrupling the life of a lithium pack. Put into real-world terms, a Tesla Model 2 rated at 250 miles per charge could theoretically cover more than 2.5 million miles before the battery chemistry breaks down. This longevity creates a fundamental shift in vehicle economics that goes beyond the obvious. In today's market, battery degradation is the invisible depreciation curve that haunts every EV transaction. A 3-year-old Tesla might show 92% battery health, and that 8% loss directly impacts resale value. Buyers discount used EVs because they're essentially buying a car with a ticking clock on its most expensive component. Aluminum-ion could eliminate this concern entirely. If a battery is rated for 10,000 cycles, and the average driver completes 50 cycles per year, that's 200 years of theoretical use. Even aggressive drivers doing 100 cycles annually would take 100 years to reach the limit. For practical purposes, the battery becomes immortal within the vehicle's usable lifespan. The ripple effects extend throughout the automotive ecosystem. Fleet operators, including taxi services, rideshare drivers, and delivery companies, currently face battery replacement as a major operational cost. A rideshare vehicle might accumulate 200 miles per day, or roughly 73,000 miles annually. With lithium-ion, that's about 7 years before significant degradation. With aluminum-ion, the same vehicle could operate for more than 30 years on the original battery. This transforms the total cost of ownership calculation. The contrast is striking. A Model 3 buyer today can expect 500,000 miles before major battery concerns. A Model 2 with aluminum-ion, if the numbers hold, would stretch that figure to 5 times higher, meaning the car could easily outlast the average ownership span of multiple vehicles combined. For a market that has long worried about EV batteries degrading too quickly, Tesla is positioning aluminum-ion as not just a short-term cost saver, but as a technology that could redefine what lifetime battery actually means. There's another dimension worth considering: environmental impact. Battery production carries significant carbon debt, including the environmental cost of mining, refining, and manufacturing. A battery that lasts 5 times longer effectively spreads that carbon debt across 5 times as many miles, dramatically improving the lifetime emissions profile. According to research from the International Council on Clean Transportation, battery manufacturing represents about 35% to 40% of an EV's lifetime carbon footprint. Quintupling battery life reduces this proportion to roughly 7 to 8%, making EVs substantially cleaner across their full life cycle. The secondary market implications are equally profound. Today's used EV market is constrained by battery anxiety. Buyers worry about buying someone else's degradation problem. With aluminum-ion's extreme longevity, used Model 2s could command stronger resale values, making EV ownership more financially accessible to budget-conscious buyers who rely on the used car market. If aluminum-ion delivers on these longevity promises, it changes everything. Would you keep the same car for 20-plus years if the battery was guaranteed to last? Comment the keyword 20 years if you'd drive one vehicle for decades with 0 battery concerns. Comment the keyword more if you prefer switching cars every few years, regardless of battery life. Share your perspective below. Are you a car-for-life person, or do you crave the latest models? 2. Why does energy density matter less than you think? Energy density is the first number most engineers and buyers look at, and here aluminum-ion faces an uphill battle. Current estimates put these cells at 160 to 200 watt-hours per kilogram, while modern lithium-ion NCM packs used in Tesla's Model 3 or Hyundai's Ioniq 5 deliver closer to 250 to 270 watt-hours per kilogram. On a practical scale, that gap means a 50 kilowatt-hour aluminum-ion pack would store roughly 8 to 10 kilowatt-hours less energy than an equivalent lithium pack, translating to about 30 to 40 fewer miles of driving range. But here's where conventional wisdom breaks down. Energy density has been the dominant metric because lithium-ion charging speeds forced it to be. When you're stuck at a charger for 30 to 45 minutes, every mile of range becomes precious. You need to maximize distance per charge because each charging session is a significant time investment. Aluminum ion fundamentally changes this calculation. Consider the parallel with smartphones. Early iPhones prioritized battery capacity because charging was slow and inconvenient. As fast charging improved, manufacturers started reducing battery sizes because users could top up quickly throughout the day. The same psychology applies to EVs. If charging takes 10 minutes instead of 30, that 30-mile range deficit becomes nearly irrelevant for most driving patterns. According to U.S. Department of Transportation data, 95% of car trips are under 30 miles. For the vast majority of daily use cases, you're never approaching the battery's limit. The critical moment is road trips, and this is where aluminum-ion speed advantage creates a paradigm shift. During a 500-mile journey, you're not comparing 250 miles versus 300 miles of range. You're comparing total trip time, including charging stops. But the story doesn't end with raw capacity. The advantage of aluminum ion is not how far you can drive per charge. It's how quickly you can refill. Lab results and early prototypes suggest a 0 to 100% recharge in just 10 minutes. Compare that with Tesla's current supercharger 5.3, which still takes around 30 minutes to move a lithium-ion pack from 10 to 80%. The gap is even more striking when you look at controlled testing. Researchers at the University of Queensland reported that aluminum-ion cells could cycle up to 60 times faster than lithium-ion, meaning their charge acceptance is on a completely different level. Let's model a real-world scenario. You're driving from Los Angeles to San Francisco, approximately 380 miles. With a Model 3 long range, you'd need one charging stop of about 25 minutes to reach 80%. With a Model 2 having an aluminum-ion battery, you'd need 2 stops, but at 10 minutes each for a full charge. The total charging time of Model 3 is 25 minutes, and Model 2 is 20 minutes. Despite having lower energy density, you actually save time on the journey. The infrastructure implications are equally significant. Faster charging means higher turnover at charging stations, effectively multiplying capacity without building new stalls. If a supercharger location has 8 stalls and each session takes 30 minutes, that's 16 cars per hour. With 10-minute charging, the same infrastructure serves 48 cars per hour, which is a triple improvement in throughput. For drivers, this changes the daily math. Imagine a Model 2 with a 250-mile rating. Even if that figure is 20 miles less than a Model 3 standard range, the fact that you can add 250 miles of charge during a coffee stop instead of waiting half an hour at a charger flips the equation. In effect, the aluminum-ion battery asks, do you really need 300 miles in one shot? Or would you rather have unlimited miles available 10 minutes at a time? Here's the real question. If you could eliminate charging anxiety completely, would you trade 30 miles of range for it? Comment the keyword speed if ultra-fast charging matters more to you than maximum range. And comment the keyword range if you'd rather have the extra miles. Tell us why in the replies. We want to understand how you actually use your vehicle day to day. 3. Why is aluminum the economic breakthrough that EVs have been waiting for? The economics behind aluminum ion may be just as disruptive as its chemistry. Raw aluminum is among the most abundant metals on Earth, costing 15 to 20 times less than lithium on a per-ton basis. That fundamental difference cascades through the supply chain and directly impacts the price of every kilowatt-hour of storage. Current estimates place aluminum-ion packs at roughly $60 to $70 per kilowatt-hour, less than half of the $130 to $140 it takes to produce a comparable lithium-ion unit today. To understand why this matters, we need to examine the supply chain vulnerabilities that have plagued lithium-ion. Lithium extraction is concentrated in a handful of countries, including Australia, Chile, China, and Argentina, controlling roughly 90% of global production. This concentration creates geopolitical risk and price volatility. Between 2020 and 2022, lithium carbonate prices surged from around $6,000 per ton to over $70,000 per ton, nearly a 12 times increase before moderating. These wild swings make long-term EV pricing nearly impossible to predict. Aluminum presents a stark contrast. Global aluminum production capacity exceeds 65 million tons annually, distributed across dozens of countries. The material is so abundant that aluminum is actively recycled at scale. Nearly 75% of all aluminum ever produced is still in use today. This established recycling infrastructure means end-of-life aluminum-ion batteries could feed directly back into new battery production, creating a truly circular supply chain. Scale that to a compact EV like the Tesla Model 2, which is expected to carry a 50 kilowatt-hour battery pack. Using today's lithium cells, that pack would cost around $6,500 before assembly. Replace it with aluminum-ion, and the figure drops to between $3,200 and $3,500. That is a savings of more than $3,000 per vehicle, almost entirely from the battery alone. For Tesla, the implications are clear. Battery costs have long represented up to 1/3 of an EV's sticker price. Cutting that figure in half makes it possible for Musk to keep the Model 2 near the much-publicized $25,000 target, and in some markets possibly even lower. When stacked against rivals like BYD, whose Dolphin EV sells for the equivalent of about $25,000 with conventional lithium packs, aluminum-ion could allow Tesla to compete not by shrinking margins, but by fundamentally rewriting the cost equation. For consumers, this doesn't just mean a cheaper car, it signals the arrival of a Tesla that finally hits mass-market affordability without compromising profit. Tesla Model 2 is about to launch in 2026. That gives us about 12 to 18 months to see whether aluminum-ion lives up to these projections or becomes another promising technology that failed to scale. The difference between those two outcomes will likely determine whether Tesla dominates the next decade of automotive history or becomes a cautionary telltale about betting everything on unproven technology.
Imagine flipping a switch and your world changes in seconds. Finally here, Tesla is about to introduce a new battery architecture that will be the first time ever that they are testing for an aluminum-ion battery and have achieved very genius initial impressions. Elon Musk teased it perfectly.
What we call it the structural battery, where the battery for the first time will have dual use. There are a few more elements that we won't get to today, but we will get to in the future.
1. How does Tesla redefine energy entirely by developing a new battery architecture? What if Tesla built a battery that works like a prism, bending energy to unlock impossible power? Let's meet Prism Core, the idea at the heart of 2026's revolution. Picture a 3D polyhedral architecture inspired by crystal lattice dynamics, where interlocking aluminum-ion cells shaped like dodecahedrons maximize surface area for rapid ion flow. A nano-engineered chroma-layer aluminum alloy wraps each cell, boosting conductivity by an estimated 700%, while integrated micro-actuators just 1 micron wide gently vibrate to keep ions from clumping. Think of Prism Core like a diamond. Its geometry traps and amplifies energy. This isn't just engineering, it's Tesla rewriting the laws of energy. Here's how it works. Aluminum carries a trivalent charge for 3 electrons per ion, so when those ions move through precisely channeled pathways inside a polyhedral frame, resistive losses plummet. If the geometry is right, you can direct ions like highway traffic at rush hour, and that is exactly what the chroma layer does. It behaves like a real-time traffic controller that adapts to voltage spikes and keeps electrons flowing smoothly. In theory, that cuts energy loss by up to 95%, which is why this architecture matters for families, not just labs. Less waste equals more usable power in every drive, every school run, every emergency. Why does this redefine family-friendly for Tesla Model 2? Because efficiency compounds into everything you feel day to day. A pack that targets 2,000 watt-hour per kilogram changes the math of cost, space, and safety all at once. If a 40 kilowatt hour Prism Core pack truly stores power at that density, you are talking about an effective 1,200 mile range claim per charge scenario with a system mass near 80 pounds, which is lighter than many laptops plus textbooks in a high school backpack, yet structurally stronger than a traditional pack because the cells interlock like a geodesic frame, in which lighter mass means quicker acceleration, shorter braking distances around crosswalks, and easier suspension tuning for a calm ride that keeps kids asleep on the back seat while driving home. The same geometry that stiffens the pack also resists deformation, adding another passive safety layer without eating cabin space. Do you think a 2,000 watt-hour per kilogram battery is the real game changer for the Model 2? Comment the keyword 2,000 watt-hour if you believe it is. And durability and confidence will come next. Aluminum's stable plating behavior, guided through those polyhedral channels, is built to starve dendrites of the chaos they need to grow. Couple that with micro actuator vibration, and you get uniform ion distribution, even under fast charging. In practice, that means a battery that stays predictable across winter cold and summer heat waves, so weekend plans do not depend on the weather. And because the structure is its own skeleton, service downtime shrinks. Fewer modules, fewer points of failure, faster diagnostics, the exact kind of "it just works" reliability families actually value. Sustainability is not a side note, it is the supply chain backbone. In 2025, global bauxite reserves, which is the primary ore for aluminum, were estimated around 29 billion metric tons, while global lithium reserves were about 28 million metric tons. Abundance translates to long-term availability and price stability. If Tesla's conceptual Eterna-Melt process can reclaim aluminum at 99.9% with near-zero waste, a Prism Core style pack could be manufactured with 90% less carbon dioxide than a comparable lithium-ion process, and a 40 kilowatt-hour pack could tally roughly 1.2 tons of carbon dioxide to produce versus about 2.92 tons of carbon dioxide for today's lithium-ion. Families do not feel tons of carbon dioxide, they feel lower lifetime costs, easier recycling at end of life, and the satisfaction of driving something that actually matches their values. Now, let's be direct about credibility. These are aggressive next-gen targets derived from known materials, science trends, polyhedral packing to increase surface area, trivalent ion advantages, active coatings to tune conductivity, and vibration to reduce agglomeration. The leap is not magic. It is geometry plus chemistry doing exactly what we ask of them, at scale. If Tesla brings Prism Core-like architecture to Model 2, the payoff is practical. Longer trips without planning gymnastics, fewer charging stops on busy school days, safer thermal behavior in traffic, and a compact pack that frees up cabin volume for strollers, groceries, and actual legroom. That is what family-friendly should mean in the real world. A 1,200-mile range in a pack you could carry. What if your battery were as efficient as nature itself? If that vision excites you and you want to see how the numbers stack up against today's best cells, then drop the word 1,200 below. 2. How mind-blowing are the specs that redefine what it means to be a genius? How do you fit a lifetime of power into a battery smaller than a backpack? These specs are not just game-changing, they are world-changing. Let's find out what they are. First one, Tesla has achieved Nova Core density, which targets 2,000 watt-hour per kilogram. This means a 40 kilowatt-hour pack near 80 pounds could credibly support a 1,200-mile range claim in a Super Aero Tesla Model 2 scenario. The Starweave Matrix idea, which is nano-woven aluminum fibers that behave like a high surface area sponge, explains where the extra storage would live. It is the same reason a charcoal filter captures more particles than a smooth block. More surface equals more reactions per second. If the weave reduces internal resistance while multiplying active sites, the math that beats a 60 kilowatt hour and 300-pound lithium-ion pack at roughly 300 miles stops sounding like hype and starts sounding like engineering. Next, flash pulse charge is where skepticism should be loudest, so let's stress test it. A 5-minute full charge implies roughly 1,200 kilowatt peak power for a 40 kilowatt hour pack. That is substation territory. The only way this fits today's world is with station-side energy buffers, exactly what a 10 megawatt hour megapack can do. Soak up energy off-peak, then dump it in short bursts without frying the local 1 to 2 megawatt feeder. A teraflow electrolyte that raises ion mobility by several-fold is the battery side requirement. A smart grid handshake that speaks to the charger and meters the spike is the grid side requirement. Add time warp AI that reads your calendar and location, pre-positions energy in the buffer, and your 1,200 kilowatt headline suddenly has a real-world workflow, not just a number. Longevity must match speed, or families will not trust it. And this is where the third spec comes out. The Eon cycle framework stakes out 30,000 cycles, which pencils to about 6 million miles, or roughly 40 years. That only sounds outrageous until you pair 3 ideas. Charge gentler because resistance is lower. Keep chemistry orderly by pulsing microcurrents to refresh cathode structure, and prevent hotspots so nothing ages faster than its neighbors. If the architecture holds 99.5% capacity after brutal fast charge schedules, you do not need a giant cooling loop. A minus 94 degrees Fahrenheit to plus 338 degrees Fahrenheit operating band is aggressive. But the logic is clean. Less waste heat plus uniform current paths equals fewer thermal events to manage, which also means fewer parts and about 40 pounds saved in thermal hardware. Regarding the fourth space, intelligence is the silent range extender. A MindLink processor that watches grip pressure, eye flicker, and heart rate can infer whether you are calm or hurried, then pre-bias the inverter and thermal targets. If that trims throttle spikes and coasts earlier without you noticing, a 40% real-world range boost is not magic. It is coaching you without nagging you. Your battery does not just drive, it feels your vibe. In American everyday life, that means fewer stops on the school run loop, less hassle when you are late to a doctor's appointment, and more miles left when you surprise visit the grandparents. Finally, cost completes the picture. A micro-cost revolution at $1,800 per pack enables a $10,000 Model 2 base, only if manufacturing hits near-perfect yields. Quantum Smith laser-guided assembly targeting 99.9999% precision is not sci-fi. It is what semiconductor fabs already chase. If scrap falls and modules drop from the bill of materials, total ownership can realistically fall by 80% over 25 years compared with legacy gasoline ownership, about $50,000 versus roughly $10,000 in energy and maintenance. Pair that with abundant aluminum supply and efficient recycling, and the price story has legs, not just headlines. Now the sanity check. None of these targets violates physics on its face. They demand tight geometry, fast ions, smart buffering, and ruthless manufacturing discipline. When you see 2,000 watt-hour per kilogram, 1,200 kilowatt charging, 30,000 cycles, and a sub-$2,000 pack in one place, the right response is not blind belief. It is, show me the pathway. We just did. Materials with massive surface area, electrolytes tuned for speed,
Grid buffers that burst, algorithms that anticipate you, and factories that hit yields the way chips do. Do you think this is how genius stops being a slogan and becomes a spec sheet for the Tesla Model 2? Drop the keyword genius below if you absolutely believe this.
New leaks point to a battery crossroads for Tesla's $25,000 Model 2. Two very different blueprints are in play: aluminum-ion and sodium-ion. Both sit among the most advanced technologies in modern battery manufacturing, and each could shape how this car charges, drives, and ages over time, all of which could affect your choice of daily drive, from short city hops to long highway runs. We look at real charging windows instead of lab sound bites. We map pack size to dollars per kilowatt hour, so you can see how Tesla could hold the line at the showroom price. We check how each chemistry handles heat, cold, and repeated fast charges. We also cover end of life, second life for energy storage, and what those pieces mean for your long-term costs. By the end, you will know which path matches your driving and Tesla's 2026 build plan. What makes aluminum-ion and sodium-ion batteries contenders for the 2026 Tesla Model 2? Tesla is reportedly testing two radically different battery technologies for its upcoming $25,000 Model 2, and early leaked data gives us a glimpse into their potential performance. The aluminum-ion battery, a next-gen development by Tesla engineers, promises ultra-fast charging that could replenish 80% of its capacity in as little as 10 minutes, far outpacing the fastest lithium-ion packs currently on the market, which typically require 30 to 40 minutes. Laboratory estimates suggest a single Al-ion pack could deliver up to 1,000 miles of range per charge, translating to roughly 1.5 times the distance of today's standard Tesla Model 3 long-range battery. Its projected lifespan is astonishing, with internal leaks pointing to 27 years of usable life, or over 10,000 full charge cycles, a level of durability no mass-market EV has yet achieved. Safety is another critical advantage. Crash test simulations indicate that punctured Al-ion cells rarely exceed 120 degrees Celsius and do not enter thermal runaway, drastically reducing fire risk compared to conventional lithium packs, which can reach 500 to 600 degrees Celsius in similar scenarios. The trade-offs are clear. Aluminum-ion has lower volumetric energy density than lithium, requiring a slightly larger pack to match comparable range, and production costs remain high due to exotic aluminum-titanium alloys and precision assembly. Meanwhile, Tesla is also experimenting with sodium-ion batteries, positioning them as a cost-effective solution for mass-market adoption. Sodium-ion packs rely on abundant, low-cost sodium, enabling production at a fraction of the cost of lithium or aluminum-ion cells. Energy density is moderate, roughly 160 to 180 watt-hours per kilogram, compared to 250 to 270 watt-hours per kilogram for typical lithium-ion, and estimated 220 watt-hours per kilogram for Al-ion, making them adequate for daily city driving or regional commutes, but less suited for extended trips without frequent charging. Charging speed is slower. Current lab reports from GMG of Australia and BTRL4 indicate a full charge could take 60 to 90 minutes under standard DC fast charging conditions. Lifecycle projections show roughly 3,000 to 5,000 full cycles before noticeable capacity loss, far below aluminum-ion, but comparable to entry-level lithium-ion packs. While sodium-ion cannot match Al-ion in longevity or rapid charging performance, its low cost and material availability make it an appealing choice for Tesla if the goal is to produce tens of thousands of Model 2 units at a $25,000 price point. Which battery would you pick for your Tesla Model 2? Comment 1 if you would choose aluminum-ion. Comment 2 if you would go with sodium-ion. Or are you thinking about another option? Share your reasons in the comments. Do you value speed, range, and durability more, or affordability and convenience? How do aluminum-ion and sodium-ion compare directly for the 2026 Tesla Model 2? Looking beyond basic specifications, aluminum-ion batteries stand out for their long-term efficiency under sustained high loads. Internal Tesla leaks suggest that after extensive highway driving at 120 kilometers per hour, over distances exceeding 400,000 kilometers, Al-ion packs retain over 85% of their initial discharge efficiency. demonstrating remarkable consistency even in extreme conditions. Sodium-ion packs, by contrast, begin to show gradual capacity fade under continuous high-temperature operation, particularly during summer or extended high-speed use, although performance remains adequate for typical daily commuting. In terms of real-world application, aluminum-ion is engineered for drivers who rely on their Model 2 for frequent intercity trips or multi-day journeys, where ultra-fast charging and consistent long-term output can significantly reduce travel downtime. Sodium-ion, with its simpler thermal management needs and lower cost, is more suited to urban driving, short routes, and frequent stop-and-go patterns, where rapid recharge is less critical. The driving experience further highlights the differences. Vehicles equipped with aluminum-ion maintain steady power delivery at near maximum output even when energy reserves fall below 20%, ensuring predictable acceleration on highways and steep inclines. Sodium-ion vehicles may experience a slight reduction in peak performance as the battery discharges, potentially limiting acceleration by an estimated 10 to 15%, but they make up for it with affordability and accessibility, enabling more buyers to enter the EV market. From a maintenance perspective, aluminum-ion packs reduce service frequency due to their structural resilience, allowing Tesla to extend intervals between software recalibration and thermal system checks. Sodium-ion packs, while easier to replace and scale for mass production, will likely require mid-term battery replacements after roughly 3,000 to 5,000 full cycles, creating modest ongoing maintenance costs for owners. Can either chemistry actually make Tesla Model 2 hit $25,000? Specs create excitement, but factories decide what ships. If the sticker is $25,000, the battery has to land at a price that leaves room for body, powertrain, electronics, software, logistics, and a healthy margin. A simple way to frame it is to set a pack cost window that keeps total cost of goods in check. For a compact Tesla at this price point, the pack usually needs to sit roughly in the $2,500 to $3,500 range to keep the business case intact. With that context in place, drill down to pack size and dollars per kilowatt hour. If Model 2 targets a 42 to 48 kilowatt hour pack, you can map the math directly. At $60 per kilowatt hour, a 42 kilowatt hour pack is about $2,520, and a 48 kilowatt hour pack is about $2,880. At $75 per kilowatt hour, those become roughly $3,150 and $3,600. At $100 per kilowatt hour, you jump to about $4,200 and $4,800. The takeaway is clear: to hold the line at $25,000 without robbing content elsewhere, Tesla needs pack-level costs closer to $60 to $75 per kilowatt hour, with a pack around 45 kilowatt hours. That brings us to chemistry choice. Sodium-ion is the pragmatic path if the goal is volume in 2026. Sodium is abundant, cathodes avoid nickel and cobalt, and the pack architecture looks familiar with prismatic formats and conservative thermal loops. Most importantly, a scaled sodium-ion line has a realistic pathway into the $60 to $80 per kilowatt-hour band, which fits the cost window above. Energy density in the 160 to 180 watt-hours per kilogram range is workable for a city-first compact, and charge curves can be tuned for durability while still delivering acceptable road trip stops. On the other side, aluminum-ion is the performance headline that still has to clear the factory hurdles. New current collectors, different electrolytes, and tighter tolerances introduce fresh tooling, fresh quality gates, and a learning curve that takes time to stabilize. Early yields and scrap can keep effective pack costs elevated. If aluminum-ion enters automotive production above roughly $100 per kilowatt-hour in the first waves, a 45 kilowatt-hour pack would land near $4,500. That number can work only if Tesla finds savings elsewhere, or positions aluminum-ion as a higher trim with a price offset. Seen through that lens, the cost targets that make a $25,000 Model 2 feasible point toward sodium-ion for the first million cars. Aluminum-ion can still play as a halo or a later refresh. Once yields, warranties, and supplier learning curves bring the effective pack cost down into the same $60 to $75 per kilowatt-hour corridor. In other words, sodium-ion secures the price and schedule, while aluminum-ion preserves the upside once manufacturing confidence catches up. After 200,000 miles, what value remains? Range and charge time shape the purchase, but end of life shapes the story you tell years later. Here, the two chemistries diverge in ways that matter to regulators, fleet buyers, and anyone who cares about total cost. Aluminum starts with a recycling advantage. Recovered aluminum typically saves about 95% of the energy required to produce primary aluminum. That means lower embodied emissions for pack hardware that already uses a lot of aluminum in enclosures, bus bars, and current collectors. It also means stronger scrap value at end of life, which helps the economics of take-back programs. Sodium-ion earns points on the front end. The bill of materials avoids lithium, nickel, and cobalt, which reduces exposure to volatile pricing and simplifies compliance for mineral sourcing rules. On the back end, sodium-ion recycling is newer, but the chemistry's lower intrinsic metal value can actually reduce theft risk and simplify logistics for returns. As pack prices fall toward $80 per kilowatt-hour, the case for second life grows. A retired 50 kilowatt-hour pack with 70 to 80% remaining capacity becomes a practical building block for stationary storage where space is abundant and energy density matters less than price and cycle stability. This is where grid use cases come into focus. Decommissioned EV packs can support peak shaving at depots, buffer fast chargers at highway sites, or stabilize microgrids at commercial buildings. Sodium-ion fits well here because moderate energy density is not a penalty inside a container, and the chemistry's tolerance for wider temperature windows can simplify the balance of the plant. Aluminum-heavy designs contribute at the same time through a tight materials loop. Every kilogram that returns to the smelter cuts the energy and carbon cost of future pack hardware and reduces the net footprint of the original car. For owners, the practical signal is total cost over 12 to 15 years. Sodium-ion's likely lower new pack price reduces replacement anxiety for taxis, ride-hail, and dense urban fleets. Aluminum-rich packs may carry a stronger scrap value and a clearer circularity story at the end of service. Put together with falling pack costs and better reverse logistics, the 2026 Model 2 could be the first $25,000 EV where the end-of-life plan is as compelling as the launch spec sheet. That closes the loop and turns a purchase decision into a full life cycle win. That wraps up our deep dive into the Model 2 battery question. Aluminum-ion and sodium-ion both look promising, and the real story will be how Tesla balances price, performance, and scale in 2026. Before you head out, tell us how you actually drive. Daily city runs, weekend highway trips, or fleet duty. Share your mileage, charging habits, and target range in the comments, and we will use your real cases in a follow-up breakdown with fresh simulations and cost math.
Thanks for spending your time with autogearshift. If this brought you value, save it, share it with someone choosing their next EV, and make sure you're subscribed so you never miss what's coming.